Welcome to this explainer. Today, we're going on a bit of a journey. We are going to trace the incredibly precise mechanical and physical life cycle of nuclear power. We'll follow the whole process, from literally pulling raw uranium out of the dirt, down into the mind-bending quantum physics inside the reactor core, and all the way out to electricity generation and long-term storage. Right off the bat, to really grasp the sheer scale of this system, you have to look at the energy involved. Splitting just a single uranium-235 nucleus releases a massive 200 mega-electron volts. To put that into perspective, if you were to totally consume just one single kilogram of uranium-235 over the course of a day, that translates to 950 megawatts of continuous heat. Capturing that kind of extreme power density and doing it safely requires a closed-loop system that is engineered to absolute perfection. So where does this cycle actually begin? Well, it starts at the macro level with extraction. Now, you might be surprised to hear this, but uranium is actually about 500 times more abundant than gold. It's just sitting there in rocks, soil, and even seawater. To get it, operators use open-pit mining, underground mining, or something called in-situ leaching, which is basically where the uranium is safely dissolved directly out of the ore while it's still in the ground. Now, obviously, you can't just toss raw earth into a reactor. It requires some highly engineered preparation. First, that mined ore gets refined down into these small, hard ceramic pellets. Then, those pellets are stacked into long, completely sealed metal fuel rods, which are specifically designed to handle extreme temperatures and pressures. And finally, over 200 of these individual rods are bundled together to form a single fuel assembly. That assembly right there, that is the highly engineered engine of our power grid. Okay, let's zoom way in. Once those assemblies are inside the reactor, the whole thing is driven by a core physical process: nuclear fission. Very simply, fission is the splitting of a heavy, unstable atomic nucleus into lighter elements. When that split happens, it kicks out extra neutrons and releases a massive burst of kinetic energy. But you might be wondering, where exactly does all that intense heat actually come from? Well, think of atomic binding energy kind of like powerful magnets. Splitting a heavy uranium nucleus creates lighter elements that are actually bound much more tightly together. And because they're bound tighter, they don't need as much energy to hold themselves together. So that surplus energy, it gets violently released, shooting those elements away at super high velocity. And all that friction as they smash into other atoms in the fuel, that's what generates the massive heat. Here is a totally wild physics catch, though. The neutrons that shoot out during fission are moving incredibly fast. But fast neutrons are actually terrible at splitting other uranium atoms. It's counterintuitive, right? But if we physically slow those high-speed neutrons down, we actually increase the probability of them triggering another U-235 fission by a factor of nearly 500. So, to manage this invisible, high-speed chaos, the reactor core relies on 4 essential components working perfectly together. You have the fuel, which is our uranium-235. You have the moderator, very often just water, whose entire job is to physically slow down those fast neutrons. Then there's the coolant, which constantly sweeps away that massive heat. And finally, the control rods. These are made of materials like boron or cadmium, and they basically act like giant sponges to absorb any excess neutrons. If you track the spatial flow inside the core, it's almost like a giant pinball machine. A fast neutron shoots out of a fuel rod, hits the moderator, bounces around, and loses a bunch of its speed. Now that it's a slow neutron, it can re-enter another fuel rod and easily trigger a brand new fission. But if the reaction starts creating too many neutrons, the operators just insert the control rods, which safely absorb the extra neutrons and immediately halt the splitting. Now, this brings us to the ultimate goal of this delicate balancing act: criticality. I know, when you hear the word critical in a sci-fi movie, it usually means something is about to blow up. But in real nuclear engineering, criticality is exactly what you want. It's the perfect equilibrium state. It simply means that for every single atomic split, exactly one neutron survives to trigger exactly one more split. The chain reaction isn't dying out, and it's not expanding out of control. It's just a perfectly steady, sustainable state of continuous heat generation. Okay, so we've got all this incredible heat. How do we harness it? Well, in the US, commercial plants are what we call light water reactors, meaning they use normal water as both the coolant and the moderator. But there are 2 main ways to do this. In a boiling water reactor, or BWR, the water boils directly right there inside the core. But in a pressurized water reactor, a PWR, the system is kept under such intense pressure that the water never actually boils. Let's compare those real quick. In a BWR, the water boils in the core and that steam travels straight out to spin the turbine in one single loop. Pretty straightforward. But a PWR takes a different approach. It takes that superheated, highly pressurized liquid water and sends it to a heat exchanger. That heat exchanger boils a totally separate, secondary loop of water into steam. This is absolutely crucial because it means the primary, radioactive coolant flowing through the reactor core is kept completely physically isolated from the power-generating turbine. Now, you might be wondering, how do you actually turn one of these things on after a refuel? Waking up a cold reactor is an insanely controlled process. It's basically broken down into 4 main phases: plant heat up, the criticality approach, low-power physics tests, and finally, generator synchronization. Step 1 is actually pretty surprising. Before any nuclear chain reaction is even allowed to start, the plant has to be heated up. And they do this using massive 6-megawatt reactor coolant pumps. The pure kinetic friction of the water just flowing forcefully through these giant pumps physically heats the entire primary system up to 275 degrees Celsius. And they do this at a painstakingly strict rate of exactly 30 degrees per hour, just to ensure there's absolutely no thermal stress on the metal piping. So once the plant is physically hot, we move to step 2, the criticality approach. Operators begin delicately, incrementally withdrawing those neutron-absorbing control rods, or they slowly dilute the boron in the water, and I mean slowly. After every single micro-adjustment, they pause. They watch the neutron count rate on their detectors, and they repeat this methodical process until the chain reaction finally wakes up and becomes self-sustaining. Once it's running, they run extensive low-power physics tests just to be absolutely sure everything is perfect. Then, operators ramp the thermal power up to about 10 to 30%. At first, all this massive steam heat actually bypasses the turbine entirely. But once the system is totally stable, they execute the final step, synchronization. The steam is finally directed into the massive turbine blades, spinning the electrical generators so it perfectly syncs up with the frequency of the power grid, and boom, we're making electricity. But of course, the cycle doesn't end there. After a few years, that fuel gets depleted and has to be replaced. This spent fuel is highly radioactive and incredibly hot, so it's immediately moved to an on-site spent fuel pool. By keeping these assemblies deep underwater, the plant provides 2 absolutely vital things at once: constant cooling for the decaying heat and a perfect natural shield against the radiation. After hanging out in that wet, cooling pool for several years, the spent fuel's heat drops enough that it can be securely moved to dry storage. These are massive concrete and steel casks. The genius of these casks is that they don't require any electricity or moving parts or pumps. They're passively cooled just by natural air circulation, safely containing that spent fuel on site for the long haul. So there you have it. From moving massive amounts of Earth, to physically manipulating atomic binding energy, to generating vast megawatts of electricity, and finally safely storing the byproduct, it's just a phenomenal undertaking of mechanical engineering and quantum physics. When you consider its immense energy density and the strict precision of this closed-loop process, it really makes you wonder, is this incredible technology the most logical way to scale up and meet our rapidly growing global electricity demands? Definitely something to think about. Thanks for exploring the science with me today.